Hello everyone, this is Tveeder NLP project Trimester-2 report. My name is Yushen. In this progress report, I will cover mainly three aspects. Firstly is the previous trimester review, and secondly is the machine learning approach to this NLP sentiment analysis task, and lastly is the result visualization. Last trimester, I used the textbook dictionary method to perform NLP sentiment analysis on the Tveeder dataset across different channels. By doing the confidence interval comparison on different channels' overall sentiment score, there is evidence shows that private channels tend to have more positive sentiment score than the public channels. Then I extracted a subdataset with only sentence contents of vaccine-related keywords. By doing the time series analysis, I was able to extract the train component of the 2021 vaccine-related news sentiment score. Meanwhile, I also investigated those extreme outliers happened in 2021. By using the word cloud on that particular day's data, I found the connection between AstraZeneca's vaccine's blood clot side effect and the sentiment drop in April 2021. I also found the June 2021's sentiment drop is related to a bacterial region outbreak. Next is the machine learning approach that I'm focusing on this trimester. We can see from the graph the key difference between the dictionary method and the machine learning method. Firstly, we need to have a labeled dataset to train our model. In our case, is sentence with positive or negative sentiment label. Secondly, there will be a filter extraction phase before we feed in our text data into our model. At the end, we need to pick machine learning algorithms to fit and train the data. Then we will obtain a model that's being able to predict on the new data input. For the machine learning approach for this project, I used the Cargo COVID-19 vaccine trace dataset with sentiment annotated. This dataset has 6,000 entries of trace data that all related to COVID-19 vaccines. And it comes with three kinds of labels, where one represents the negative treat, two represent the neutral treat, and three represent the positive trees. From the left graph, we can see that the class label distribution is not that even. We got 3,500 of neutral examples and about 2,000 of positive samples, but only has less than 500 of negative samples. This imbalanced dataset is quite challenging for the machine learning algorithms to learn. The predicted outcome will bias toward the majority group, in this case is the neutral labeled text. But in fact, we are more interested in the minority group samples, which is the positive and negative sentiment. This also has an impact on my final model's performance. We will see it later on. Next, I'm going to introduce you the bag-of-words filter extraction and the TF-IDF filter extraction. They are both really popular ways of doing filter engineering. The bag-of-word method treats the text corpus as a bag of single token words, and the outcome of the vectorization will simply counting the words appear frequency in the text corpus. Where the TF-IDF is a little different. It calculates the term frequency and inverse document frequency for each word in the text corpus. Intuitively speaking, if a word appears more frequent in document A, but not so frequent across all other documents, that implies this word is very important for document A. According to TF-IDF, a larger weight will be assigned to this word. For example below, to simple sentence, the vaccine keep you healthy, and the Pfizer vaccine prevents you from getting COVID. The back of word is just a matrix that's showing the frequency of each word. The TF-IDF assigns the TF-IDF score to each word. From the document 2, we can see the TF-IDF assign a higher score for the word Pfizer than the word vaccine, because the vaccine appears also in document 1 as well. But the Pfizer word is kind of unique to document 2. Word embedding is also a popular choice of feature extraction in vector space model. It captures context and semantic of words, unlike bag-of-word model only represent number of occurrence of words without any relationships and context. The word embedding is also able to preserve the context and the relationships of a word so that it can detect similar words more accurately. From the left graph, we can see the vector represent the word queen and the word king is quite similar. We can understand the word queen is a word king minus the man and plus woman. On the right-hand side, I show how our word-to-vector vectorization preserve context and relationships. Example 1 shows that the word Australia is similar to words Japan and COVAX, which kind of makes sense because they are all countries or organizations. Example 2, the word Pfizer is similar to word Johnson Johnson and Fauci, although Fauci is a person, but he must appear quite often together with Pfizer word. That's why word embedding will think Fauci is related to Pfizer. And here is how I did the experiment. The machine learning algorithm I picked for this project are naive Bayes, random forest, and AdaBoost. I tried all combinations of experiment models by picking one feature extraction method and pick one machine learning algorithm. And then I split the data into 1 to 5 training and testing samples. I fit the experiment model with the training set. Then I comparing the experiment model with the textbook model in terms of accuracy on the same test dataset, in order to see how textbook model perform compared to the machine learning approach. After performing the experiment with different combinations, I found the best performance model is bag-of-word with random forest and TF-IDF with naive Bayes. They both have 71% of accuracy on the test dataset. On the other hand, the textbook model has a 49% of accuracy on the same test set, which also passed the benchmark if we consider a 3-label randomly guessing with 1/3 of chance of getting right. However, test accuracy does not represent everything. Let's take a look at the confusion matrix here. The way you're interpreting a confusion matrix is to see whether most numbers appear on the diagonal line. Numbers on the diagonals representing the correct prediction for each class. In our case, if we take a close look at the first row of each matrix, which is the negative label classification, we can see our machine learning models perform very bad, or I should say, in terms of predicting the negative labels, textbook is actually the best among those. But why is that? That is caused by the imbalanced dataset I mentioned before. The training dataset is severely skewed to the majority group, that causing the final model give a biased prediction towards the majority. To overcome this in future studies, there are a few options. Firstly, we can downsampling the majority group so that the whole dataset reach a relative balance. Secondly, we could add more minority samples to make the whole dataset balanced. Lastly, we could also select the one-class classification algorithm to perform the training. Since the one-class classification, we're only focusing on the target group, therefore less affected by the unbalanced dataset. Here are the 4 different methods of sentiment score movement across 2020 and 2021. We could see that in 2020, the vaccine-related sentiment is bouncing between a low range of 0 to 0.3. However, on the 2021 graph, we could clearly see an uptrend happening during the second half year of 2021. This uptrend is captured by 3 of the machine learning algorithms except the textbook. That might imply that opinion toward vaccine and COVID-19 becoming better in second half year of 2021. To investigate what happened during the second half year of 2021, I used the word shift visualization method to compare the keyword contribution to the positive and the negative side of sentiment. Here is the word shift graph below. On the left-hand side is the first half year of 2021. We can see the word care and confidence contribute most on the positive side, and the word restrictions and dose contribute to the negative side. On the right-hand side is the second half year of the 2021. It shows that the word fully and people improve the sentiment score mostly, and the word blood and risk has some negative impact on the sentiment score. From this graph, we could conclude that the first half year of the low sentiment score is mainly due to the COVID-19 restrictions, and the second half year's sentiment uptrend is somehow related to fully vaccinated or fully qualified, according to the Tveeder dataset vocabulary. That's the end of my progress report. I'd like to take this chance to thank for my professor Luis and my teammate Ziying to be so supportive. Thank you everyone, and thank you for your time.